Morning, one and all. Today I'm going to present my paper along on Leon battery temperature forecasting method, and it is a case study what we have started with now. I have a small group of my research. Myself, Dr. Vaidehi, and two students are there with whom we have started this particular project. Uh, this paper covers a deep learning inspired enabled temperature forecasting for lithium ion batteries, which basically uses time series forecasting approaches. So we have used a data set of 34 lithium ion batteries packed for this particular experimentation, as these batteries are highly utilized in many different applications because of their high energy density, high power density, low pollution, and prolonged lifespan. We have considered this type of batteries to start with. Also, moreover to that, the temperature and the electromechanical characteristics of the batteries are influenced by their thermal effects during the operation, which significantly impact on their longevity and safety. Thus, to use batteries practically, it is crucial to forecast the temperature change of the batteries in electronic devices, electric vehicles, and now we started with oil and gas industry also, where it is very crucial for us to predict the battery life when there are too high temperatures in which they are placed in. To start with my presentation, I'm going to give a little bit of introduction, then contribution, then methodology and results, where we will go through battery data description and pre-processing. Then we will take care of autoregressive integrated moving average, that is ARIMA, and long short-term memory networks, that is LSTM. Then we will go with the result analysis and conclusion. As we are targeting this particular research for the area where not too much of computational power will be available, so we have started with these small things like ARIMA and LSTM, but we do agree that there is a lot of work done in artificial neural network and DNN. So at the end, I would like to present the comparison of our algorithm with ANN and DNN. Okay, coming to the introduction. So, as I have already told, monitoring and managing battery health is crucial for enhancing the performance and lowering running expenses for electronic devices. Knowledge of probable future temperature beforehand may help us to minimize the chances of overcharging, to prevent the battery from crossing the threshold value above which battery's health characteristics might get hampered. And thus, we propose a long short-term memory. After this, I will be calling this as LSTM, and autoregressive integrated moving average, what we call it as ARIMA model, for predicting the battery temperatures. So the main contribution of what we have done till date during this experimentation is the temperature of lithium ion battery is predicted. We are in the process of prediction, and we could predict very nicely using the ARIMA based LSTM under the variety of circumstances. A real-time data set we are gathering and pre-processed to improve the data quality for effective prediction and performance. The pre-processed data are further processed for the prediction using LSTM, which can remember information for the extended periods. The performance of LSTM is improved through the use of ARIMA, which uses a series of data to provide a better understanding and a prediction process. So methodology and results. First, we will go with, battery data description and pre-processing. The data set contains time series data of 34 unique lithium ion battery types. Data has been measured at equally spaced interval of a time that are approximately 6 seconds. So these data we are taking as a directly data set which is available on the net, but we are in the process of creating our own data set on the similar lines. To compare the data, there is a metadata file that contains the information about the batteries. So fundamentally, this metadata file contains operational profiles, that is charge, discharge and impedance of 34 unique battery types. Within each battery types, there are at least 62 files at different times what they have taken into consideration. So to start with, out of this 34 unique batteries, we have completed at present with 4 lithium ion batteries, because the metadata is too huge of 62 files. In order to understand clear, we required some time. So we start with, to check whether we are on the right track or not, we start with the 4 lithium ion batteries, that is B0045 to B0048, and were grouped and subjected to 3 distinct operating descriptions like charge, discharge and impedance in an environment with a temperature of 30 degrees Celsius, because we consider it as a room temperature in India. So at a predefined load current level of 1 ampere, the discharge was forced to halt at 2 volt, 2.5 volt, 2.2 volt and 2.7 volt for each of the batteries, 45, 46, battery numbers 45, 46, 47 and 48 respectively, according to the data set what we have got. So charging was done in a constant current mode at 1.5 amperes until the battery voltage reached 4.2 volts, then continued in a constant voltage mode until the battery current dropped to 20 milliamperes. So electrochemical impedance spectrography frequency sweeps between 0.1 Hertz to 5 kilohertz range were used to estimate the impedance also. The test continued till the capacity dropped to 1.4 amperes, because we usually take 30% of the fading. So 30% of 20 milliamperes fading minus comes out to be 1.4 amperes. So as I have told, that this data is too huge, and we need to find out the readings obtained from the battery at different instances of time for charge, discharge, impedance, but the battery temperature performance during the charging and is sometimes that is present, consider it as a crucial aspect of the battery health. So we are going to consider the battery charging time. So for experimentation purpose, whatever the data we have received, the first thing what we have to do as is something like data wrangling. So there were lot of null values which were present. The data was not up to date, up to the mark. So we need to do a lot of data wrangling is done, and then followed by the exploratory data analysis, because when we talk about the battery life expectations, as it was in the second form of data, we were not having in months also. So in that particular case, out of too many parameters, we tried to reduce the parameters through exploratory data analysis, just to examine the relationship between the various features and our target variable, which was nothing but measured temperature. So first of all, we tried to apply the Pearson's correlation method, and the graph is shown over here. We found that the large correlation between the measured current, you can find it over here, the measured current, then the temperature measure and the current charge with respect to time, and there is a huge, we can find over here 0.86, that is a temperature measured. Then we have a temperature measured over here, and then current charge over here, and we have a current charge over here also. So there are two parameters which are highly correlated, and apart from that there are three parameters which we presume to be negatively highly correlated. So from this we could conclude that when we talk about something like current measured, temperature measured and current charge, this becomes a vital features for our data set. So methodology and the results, as I have already told that we are going towards the low computational power. So we started with the ARIMA. So fundamental ARIMA model for is built for this particular application, as the seasonality presently is unclear for the temperature measured. So In order to find out the seasonality, we required a huge amount of data, not only the number of a data, but we required huge number of repetitive analysis. And second is not what I can say, the parameter which can tell me the seasonality very accurately. So for implementing the ARIMA model, we required optimal values of PQD. But however, because the series index data available is in second and not in date time format, we cannot plot the seasonality graph to check the length of the seasonal period from the decomposition graph. So instead of that, we make use of predefined auto ARIMA model in Python that automatically checks the Akai information criteria, what we call it as AIC, against all the possible integration of P, D and Q values and returns the best suited P, D, Q values for the time series data given as particular as input. So this is the plotting of auto ARIMA work. This is a sample analysis for a battery. I think this is for the battery for B0045, where we have compared the ARIMA values, getting all the P, D and values over here. So you can find that this particular thing, that is ARIMA 111, and AIC is having the maximum over here, and time required is also too less. So we concluded that with the P value of 1, D value of 1 and Q value of 1, we can very better design the ARIMA model. So here I would like to clear that the P value, what I'm talking about, is the number of autoregressive term. D is a number of non-seasonal differences needed for the stationarity, and Q is the number of lagged forecast errors used for prediction. So if I talk in terms of mathematics, then as the D value is 1, then we required only a simple linear equation. That is, if I want to find out delta Y, it is something like Y at the present instance minus Y as the previous instance. So mathematically also it is giving us less computational load. So similarly, we talk about something like LSTM. In LSTM based approach, we need to consider a look back window size period for a model to consider to make forecast. By rule of thumb, this window size should be greater than or equal to 1 seasonality period. But however, again, as I have told, that it's very difficult to find the seasonal parameters over here. We tried to use a partial autocorrelation function, what we call it as PACF graph. So by trying different window size values for each battery type, we chose the value of window size that on average gives the best performance. So when we observed the PACF graph, there were high autocorrelation with many times steps in the past. So you can see this autocorrelation graph. So you can see that this is 0. We will leave 0 window size. At 1, 2, it is highly correlated. 3, 8, they are negatively correlated, and so on and so forth. So we started with 1, 2, then 3 with a negative correlation, then coming to the 9, and with that window size we started working on this. So by trial and error method. So we found that the window size of 1 to work best with univariate LSTM, and the window size of 2 to work with multivariate LSTM model. So here multivariate, we have taken only 2 variables, not more than 2. 3 LSTM layers comprise of sequential model. So each LSTM layer is succeeded by a dropout layer, and in the end by the dense layer. It is as good as a reduced version of deep neural networks. And Adam optimization, so instead of regular ReLU optimization techniques, we tried with Adam optimization algorithm is employed to determine the ideal set of parameters to reduce the cost function. We trained the univariate LSTM model on 30 epochs, while the multivariate LSTM model on 8 epochs, to learn the fine-tune data and provide the accurate results. So these are the results that these are all I have just for sample I have shown 10, but actually they are 32. On 32 we have applied ARIMA. For a single battery 32 we have for single battery 62 files we have applied for ARIMA, univariate LSTM, multivariate LSTM, and we try to compare with only a simple root mean square value in order to put a thought process in a proper line or not. And then we started counting on how many CSV files work better with ARIMA, how many with univariate, and how many with multivariate. And these are nothing but the error, mean square error plot, what we get with every epoch cycles. So this is for 0045, we could get 47 ARIMA working well, 18 univariate and 7 multivariate. So this is, I have shown only with the example of 45 battery, but when we worked on remaining 3 batteries, we found that ARIMA works better in most of the cases, and you can find it in my paper, what I have given for the publication. Like 45, 47, 48 works better with ARIMA, except 46, which is better with a multivariate LSTM. So we concluded that yes, it's ARIMA because the number variation is too high as compared to multi and single variate. And then whatever the papers are available, we compared our proposed method with them. So we can find our accuracy is 0.9, precision 0.94, recall. So everywhere you can find that it is better. But again, I can't put it on the paper that this is the best one, because we have worked with only 4 battery at present, and remaining near about 28 batteries are left over. Moreover to that, this is what we have worked with the data set available, and as we all researchers know it very well, the data set totally work differently when we actually go for the implementation phase. So but yes, for time being, these are the results what we got. So coming to the conclusion part, the ensued loss function RSME value denoted the potential to improve the model and perhaps an opportunity to test the LSTM based learning method given the nature of the batteries to somewhat eliminate the pattern based on its past value. We resampled the data to consider only features that relate strongly to our target variable, that is the temperature and the voltages, and implemented univariate and multivariate LSTM separately on all the 4 battery types that we have considered for the analysis. Based on the comparison of the performance values of 3 predicting approaches, overall charging data for that battery type, we attempted to generalize one forecasting model for each battery type. Due to time series short length and the fact that observations are collected in seconds, they may eventually exhibit seasonality, which points to a flaws in our model. It will be important to make more databases with a reasonably long time series available to address forecasting accuracy problems which are well known in the field of batteries. The drawback of multivariate LSTM forecasting is that we will need future values of the independent variables as well as to forecast the subsequent values of our desired variables. Unless we have values for the upcoming independent variable, we will only be able to forecast one time step in a future of the targeted variable. The proposed model provides 96% of accuracy with only 2% of false positive rate. The methods primarily for is a very short time series data which may reveal seasonality or other variation ultimately related to the battery chemistry also. The use cases of these applications are many in accessible areas where person cannot repeatedly intervene to record the temperature. This application can give caution warning in case the threshold temperature is going to cross the X time steps in the future. Business value is that provided there is some way to collect the temperature values of the batteries, this application can be implemented to caution the user before threshold breach. This can save time and money for the customer to prevent any system malfunctioning, take care of such a situation well in advance, and ensure smooth functioning. In future work, novel technique may be integrated into deep learning model to avoid overfitting issues which may improve its performance. So thank you for the patient listening, and these are